Okay. So, what is light? Light is a particle. It comes in chunks. We've already written this. Okay. Light's a particle. It comes in chunks. And we know that because of the photoelectric effect. Okay. The only thing that explains the photoelectric effect, the only reason why can we explain why electrons can be knocked off, is if we get little chunks of energy, and if the chunk is the right size, it knocks it off. If the chunk is the wrong size, it doesn't knock it off. Okay with that? Okay. Light's a wave. We can measure its wavelength, and it behaves as a wave, and that's what we're going to look at today. How do we know that light is a wave? Okay. So, what tells us that light's a wave? What does it mean it behaves as a wave? How do waves behave? And what can we see that proves that light behaves this way? And I'm going to say the reason why we know light's a wave is because you see a rainbow when you put it through a diffraction grating. Look through those diffraction gratings, you saw the rainbow of all the color, and then you can get specific colors that bent certain amounts, right? When I projected through a diffraction grating, we saw the rainbows on both sides. Those rainbows on both sides are proof that light is a wave. So we've got to explain. Don't just take my word for it. I don't want you to just take my word for it. So we're going to talk about how diffraction works. Okay. I kept saying that was a diffraction grating. Okay. So diffraction is when light passes through or reflects off a series of thinly spaced lines. Those little pieces of plastic you looked through, you probably couldn't tell, but there were 20,000 lines per centimeter. Our eyes aren't good enough to see 20,000 lines scratching per centimeter. Okay? Or the back of a CD or a DVD. Always see those rainbows when the light reflects off of it? That's because a CD or DVD has got all those grooves cut into it in circles. Lots and lots of lines cut into it. So that's why you see the rainbow reflection. The rainbow reflection you see is because of diffraction. And what's happening here is the waves are interfering with each other. Now, we think of interfere as getting away all the time, but to scientists, interfere means that they don't affect each other directly, but the results change because a wave going one way and a wave going another way can pass right through each other without either one of them stopping. But where the wave runs into, where the top of the wave runs into the top of the wave, they're going to pile up twice as high. Okay? So, let's see if I can give you, I'm going to give you a few examples of what we mean by interference. Okay, so this drawing is, the white line is the top of a wave, the yellow thing is a barrier with one little hole in it. So when that wave goes through that hole, what's going to happen? Well, when it goes through that hole, the wave's going to go through here, but it's not going to go through any place else. It's going to come out. When it comes out, it's going to come out as a curve. Okay? Almost as if you dropped a pebble right there in the middle. Seem reasonable? I'm not stretching the exam. I can't make this too wide or only see the edges of the curve, but it's going to curve as it comes out. Everybody agree? Okay? That is really, really boring. Now I put two holes in my barrier. What am I going to get we'll get two curves on the other side. Okay, and here's the interesting part. Those curves actually run into each other. And this is what we're talking about interference, where this wave runs into that wave. They're going to interfere with each other. And right here, the top of one wave is on top of the other, so it's twice as high right there. Does that make sense? So if each wave was 1 foot, right here it would be 2 foot. Now, right behind this, though, right here, there's going to be a low spot, right? There's going to be a low spot on the way this curve, so the high point here is going to hit the low point there. They're going to cancel each other out. Because if one goes up 1 foot, one goes down 1 foot, you end up right where you started. So the low part of one wave crosses over the high part of the other wave, they just cancel each other out. So right where the crest add up, right behind there is going to be a place where crest hits trough. And they're going to cancel each other out. And right behind it, right between the two of them, right here, is going to be a place where trough meets trough. And it's going to be twice as deep. So right in front it's twice as high, right behind it is twice as deep. You okay with that? Still, more interesting than one curve, right? But still not really how we can tell that. Now if I make several waves, I'm going to make several curves. And as those curves expand, they're going to run into each other. And they're going to run into each other in a pattern, an interference pattern. Interference patterns are proof that waves are interacting. Okay? So let's see what happens with this interference pattern stuff. Okay. Okay. So I have a way of making waves. Turn on the water, make it drop, makes a wave. And if I measure that wave, that if I put this here, and this here, once I put those waves, they draw the same wave, just out of sync. The wave hits here sooner than it hits there. But they're equal heights, right in rhythm. Anything interesting happening there? No. Okay, so let's make two waves. Come on, second one, turn on. There we go. See how the waves run into each other right along here. Oh, it turned off again, darn it. All right. So notice they run up here, and notice this part where they run into just runs right up the middle. Okay, but right next to it is a place where the high point reaches the low point, and right here the wave actually gets canceled out. So if I measure here, right down the middle, the wave's going up and down. If I put it over here, hit the right spot, it's hard to hit it perfectly. But you see that they cancel each other out. So here we call it constructive interference. The two waves are on top of each other. Here we call it destructive interference, because one wave's bottom hits the other one's top, and it gets knocked down all the time. And notice that goes all the way along this line. But there's a line all the way back. Interference. Okay. Now I'm going to turn off one of them. No, it won't turn off. Okay. Turn off. I clicked on you. Turn off. There it is. Okay. And you'll notice that now wave heights are all back in sync. Okay. Now, so it works with sound waves too. Sound waves are going to do the same thing. going to add up to the same place. So if you have two speakers giving out a steady tone, if you walk along the back wall, it will be loud, quiet, loud, quiet, loud. All right? Everybody okay with this so far? This is how waves work. Okay. Now I put a slit in my wave. Now, do the same thing, making waves, moving the whole bar forward. Whoosh, whoosh, whoosh. Okay. Make my curve. Everybody agree with that? Move it back a little bit more so we can see a little bit more of the curve. Let me move it back forward. There we go. So you can see that the waves are making the curves, right? Now I'm going to change it to two slits. Okay. Hard to see because the slit separation, the slit width is a little bit big. I'm going to drop that down. Okay. And if I take my gauges out of the place where it goes up and down and up and down and up and down, and I'll have a place where it cancels out. So this is just to say that ocean waves work the same as two drips running into each other. See how the two slits behaves just like the two faucets dripping. Okay? Everybody okay with me this so far? Okay, now what I'm going to do is I'm going to change the frequency. Okay? I'm going to make the waves closer together. And when I make the waves closer together, I still get the up and down, but notice the one up here that was canceled out before isn't canceled out anymore. In order for it to cancel out, I've got to move it in closer. So if they cancel out closer together, the higher the frequency, the shorter the wave. So close together, they cancel out. But notice, they still add up down the middle. Okay. If I make the frequency low and make the waves long, they don't even have time to run into each other before they run out of room. Now, there's a slight difference, but yeah, they just there's actually you gotta have a certain frequency before they run, so they can run into each other. If I get out here, they cancel each other out again. The angle is way over here for them to cancel out. So the longer the wave, the more it spreads out. Everybody okay with this? Okay. So, with that in mind, back here, in the back of the room, I've got a laser. Okay? Okay, so I've got a laser, and let's make sure that where the dot is going. There, it's on the, so you want to look up there. Everybody see the dot on the laser? Okay. And I got this little thing that I can slide slits in front of it. So look what happens when I put double slits in front of my red laser. Okay. Everybody see what you see up there? You see alternating dark, light, light, dark, right? Yeah. Okay. If I've got different gaps on different slits, so I don't know if this is the best one or not. And that one spreads about too far. There, that spreads out a little bit more. It's all about how close together the gaps are. But the key is that the whole key is that I see that interference pattern. That right there proves to me that light is a wave. Because only waves are going to do that. Does that make sense? Okay, so what's showing up on the screen and what's showing up on the wall are the same thing. Dark, light in the middle, a dark spot, light further out, a dark spot. So that right there is proof that light's a wave. Okay? Proof that light's a wave. Okay? So, what happens if I use light? So this is the experiment we just did. I only had a red laser. Okay? And it was set up so that it would block top and bottom, so it had a slit. Normally, if I aim it at things at one point, it diffracts round. And notice what happens when I make the wavelength shorter. Seems to be moving closer in, doesn't it? Okay? And here's why. Okay? So, same idea, light comes in, got two slits, and if the light is green, notice it adds up down the middle, and then there's a dark area, and it adds up further out, there's a dark area. The red dots we just saw. Did we look at that? And as I change the wavelength, they add up further out, the more red it is, and they add up closer together, the more towards violet I make it. Okay? And that's when I project, that's why when I projected the rainbows, you could still see the white light down the middle, because every color is going to add up down the middle. Right? But then the first one that's going to add up outside of that is going to be purple. And then further, a little bit further out, the blues will add up. Where's my mouse? A little bit further out, the blues will add up. You see that? You see blue in your rainbow. When you see green in the rainbow, you're seeing where the greens add up. Okay? When you see yellow, that's where the yellows add up. When you see reds, that's where the reds add up. And once you get to the end of the reds, right here, there's another purple. Because purple, you go right, because purple, right here, there's going to be another purple. And the purple add up for the second rainbow. And then it'll just keep building out as you go. So the fact that you see a rainbow is proof that light is a wave. That's the big picture. Rainbows are this pattern of alternating light and dark is proof that light's a wave. So, light shows interference pattern, light is a wave. So on Thursday, I showed you a whole bunch of experiments that said light is a particle. Now I just said everything else I've showed you is proof that light's a wave. The reason we saw those lines of color from those glowing gases was because light's a wave. Okay? So, what will an electron do when going through two slits? Because if light is both a particle and a wave, an electron's a particle. Is it a wave? Yeah. Okay, so there's two possibilities. If you send an electron through two slits, if it's a particle, it has to go through one slit or the other. It can't go through both. Remember bowling on Friday. And the bowling example from Friday. The bowling ball either had to go through one side or the other, and you were never going to be able to get a strike because you would never get the head pin. It could never go down the middle of the alley. Right? Or will it go through both slots at the same time and make an interference pattern? Now, one of the difficulties is you have to get something smaller than the wavelength of light for your slits. Okay? So I had to find some pretty narrow slits. They want to check this, but that's one of the difficulties. So the movie used bowling balls. Okay, I'm going to use an electron gun. Okay, if the electron is a particle, it will either go through one slit or the other slit. No matter how many times I fire this gun, it's going to go through one slit or the other. And the safest place to stand is right here, if you don't want to be hit by an electron. Everybody, so I would not even have to look at any of this. If I just looked right here, the fact that I only saw two spots where things were hitting would tell me that that was a particle. Because that's what a particle will do. A particle will go through one hole or the other. If the electron's a wave, it goes through both slits at the same time. And over time, as you keep sending electrons, it's hard to detect one, you get a pattern over on the wall. Alternating patterns of light and dark. With the place where they hit most often, right behind the wall. Behind the wall is the dangerous place to stand if the electron's a gun. Okay? Between the slits is the dangerous place to be if you want to build a house on the beach. Because the waves are going to be twice as high there. You're going to wash your house away. Okay? So, this is the experiment they had. If I pass an electron through slits, which one is it going to do? Okay? Now, they had to find some slits that were small enough. What they found was the gap between aluminum atoms in a crystal of aluminum. Piece of aluminum. So they shot X-rays through aluminum, and X-rays are light, so we know it's waves. And then they shot electrons through aluminum. And they looked at the pictures they got. Okay. Okay. X-ray in aluminum foil. Notice, because I can't get a horizontal beam, you get the round part, just like the animation showed, but I go dark, then light, then dark, then light, then dark, then light, then dark, then light. Interference pattern. X-rays are a wave. They're doing just what white light does. Makes an alternating pattern of light and dark. Okay? Second picture. That's an electron. That's what happened when they shot electrons at aluminum. Shot electrons at aluminum. They got a light ring and they're dark, a light, dark, light, dark. Can you everybody see how these two pictures are similar from each other? Similar to each other? Okay. So if the one on the left says X-rays are a wave, the one on the right says electrons are a wave. It's the diffraction pattern. Electrons are waves. Gravity check. Yep, still working. So this is what led to Schrodinger's equation. Sometimes you see Schrodinger spelled with an E after the O. I think it's supposed to be the umlaut. And actually, treating the electron as a wave answered one of the questions that Bohr couldn't answer. One of the questions he asked Bohr, Bohr said, the electron can have this much energy or can have that much energy. It can never have the energy in between. And if you asked him why it can't have that energy in between, his answer is because it's not allowed. If you ask why is it not allowed, is because it never has that much energy. Everybody see the flaw in that argument? Okay. He knew from the light that it had energy levels, but he didn't know why. But if you treat electrons as waves, that problem goes away. Okay. It's hard to model the 3D waves that they actually are, but I'm going to try to make waves that the kind of waves we're talking about. Now, the kind of waves we're talking about are called standing waves. They're like the vibrations of a stringed instrument. I get this. Try to some stuff in my way. Okay, so let me see if I can make a wave with this chord. Okay. Okay, so I got a wave there, right? It keeps going up and down and up and down. It's not going anywhere. A standing wave, like a jump rope. But if you change the frequency just a little bit, that's too fast. Right. You can make 2 waves. Or 3. Okay? Or that's just 3, isn't it? Darn it. Okay. Can I do 2.5? Is 2.5 an option? How about 2.25? How about 2.1? It's got to be 1 whole wave or 2 whole waves. It can never be in between. An electron has to be on the first energy level or the second energy level. It can never be in between. So energy levels are not little rings like Bohr said they were. Energy levels are waves, standing waves. You either have 1 whole wave or you have 2 whole waves. You're never going to be in between, including when you switch from 1 to 2, because you can't gradually go from 1 whole wave to 2 whole waves along the way. It has to stop being 1 wave and start being 2 waves all at once. Okay? And they don't look like this. Right? They don't look like this. They're 3-dimensional waves, 3-dimensional disturbances, but you get the idea that you could either have 1 wave or 2 wave. You can't have 1.7. All right, that? So electrons are waves. So Schrödinger wrote the equation of the wave. Okay? And that is where we get the quantum mechanical model. I am done misleading you. This is the current version, the current model of the atom. The current model of the atom, the quantum mechanical model. So earlier we said that light was energy. Energy came in little chunks called quanta. Energy comes in little chunks called quanta. So the quanta is the amount of energy to go from one energy level to another, which is not actually going from one ring to the other, but going from 1 whole wave to 2 whole waves, or from 2 whole waves to 7 whole waves. So how the quanta work? Quantum mechanical. The mechanics of those quanta moving around. How those quanta move around is the quantum mechanical model. How those little chunks of energy move around. That's why they call it that. How do little chunks of energy move around? How they get to be 1 wave versus 2 wave. Okay, so Max Schrödinger derived an equation that described the energy and position of the electron in an atom. We've got some good news and some strange news. Good news. You are never going to have to solve Schrödinger's equation in my class. Okay. That's because I never saw it until my 4th semester of calculus. I talked about it on my chemistry classes, but they never showed me the equation until my 4th semester of calculus, because it doesn't mean anything until you've taken 3 semesters of calculus. You guys probably aren't ready yet. And so they're okay with why you're not going to have to solve it. And here's the strange part. I said it was really strange. Why they brought it up in my calculus class was the first thing we did was prove that you cannot solve it. Which means you can never say where an electron is and how much energy it has. Which says, oh, it's a bad equation. No, that's how the world works. You cannot tell where an electron is and how much energy it has. Okay. The next thing we did was we learned that if you square a function and treat it, to go through a special algebraic process, you can tell the chances that the answer is between here and here. There's a 50% chance the answer is between these two numbers. It's a mathematical trick. Well, you don't get the exact answer, but you tell where you're likely to find the answer. So first we proved you can't solve it exactly, and then we said even though we can't say it exactly, we can still say where there's a good chance of finding an answer in between these numbers. Okay? The equation was the equation of a wave. A 3-dimensional wave, which is kind of hard to predict because we never see 3-dimensional waves. You can't picture it. Oh, we're running into things we can't picture. Yeah. Quantum mechanics is strange because we can't picture things behaving the way that the math says they do. And then we check the math, we find out the math's right, and they've done some bizarre stuff. Okay. So quantum mechanical model is a mathematical solution. But it's not like anything you can see. I mean, you write the equation for a parabola. You could draw the parabola, okay? And you would say, hey, that's a parabola. This is not that way. Okay? And it's going to behave in ways you can't see, which is, I mean, if you listen to the video, the people whose job it was to explain quantum mechanics say things like, I don't really understand it that well, because it's not intuitive. Hard to come up with analogies in your everyday life. Okay. It's got energy levels for electrons, but they're not the nice little circles that Bohr drew. They're waves. The energy level turns out to be 1 wave or 2 waves. Okay. So when we talk about Bohr, we talk about orbits. When you did your reading of 5.3, they talked about orbitals. Different things. And what you get, when you square the function, you can tell the probability is between these numbers, and that's the best we're ever going to do. We're never going to say where the electron is. We're going to say where we have a chance of finding the electron. So we're not saying where the electron is. We're saying where we have a chance of finding it. We're going to slip and say things like the electron is in a p orbital. But a p orbital is just a region where you have a chance of finding it. So the electron is where you have a chance of finding it. And that sounds like a lot like our model of the atom when we left Rutherford. Okay, remember we left Rutherford. We had the electron cloud, right? To him, it was a cloud because it was a cloud of uncertainty. He had no way of knowing where the electron was outside. For them, the electron cloud is where you have a chance of finding an electron. Isn't that how we defined it? But now it means something completely different. It's not because of bad tools. It's because that's the best we're ever going to do, is say where we have a chance of finding the electron. Because the electron's a wave. Could you ever point to a wave? Could you put your finger on an ocean wave? Like you put your finger on a part of it. The crest, you follow the crest along with your finger, right? But you couldn't do one wave. You couldn't say the wave is here because there's going to be an end on both sides. So even a simple wave, saying where it is hard. Right? With electron waves. Now, if you do the math, you could do the math to find out the chances that an electron in a carbon atom at the end of my nose is just outside that door. You could do that math. And the chance would not be zero. It would be incredibly tiny. But it wouldn't be zero. So we can't even draw shapes that include 100% of the chance. Because if we try to include 100% chance of finding the electron, all we have to do is select the entire universe. That doesn't give us much information, does it? So what they do is they draw a line at 90%. They can draw the same line at 95%. It's just going to make their area a little bit bigger to get that extra 5%. So that's why. So we're going to change the definition. We got a problem with electron cloud because this is where all the electrons are. To understand it, we can't talk about all the electrons at once. We need to talk about one electron at a time. Okay? And we want to talk about all the electrons. All the electrons when you talk about the electron cloud. But if we want to talk about specific electrons, you need to talk about atomic orbitals. And this is that word I tried to warn you about. Okay, orbit is the circles for Bohr. Orbital, they stole the orbit word from Bohr, but it's not those nice circular orbits. Okay, let's have to see what they are. Well, if you look at Schrodinger's equation, there are actually 4 coefficients that show up in the middle of it. Okay? And one of those coefficients is the principal quantum number. And the principal quantum number will tell you how many waves there are. 1 wave, 2 wave, 3 wave, 4 wave. Okay? Which means energy level. Because if the whole wave solves the Bohr problem, why can't it be in between? Because it's got to be 1 wave or 2 wave. It can never be 1.5 or 1.7. Because 1.7 wouldn't be still. Okay? But inside each energy level, the math draws different shapes. There's more than one type of whole wave. And those are the atomic orbitals. So And if you look up the definition of atomic orbital, they're going to say the definition is region where there's a high chance of finding an electron. But wasn't that just the definition that you wrote for electron cloud? It's the same definition. How can the same definition apply to two different things? Well, it's simple. Electron cloud is where you have a chance of finding any of the electrons, or all the electrons. Somewhere in here, you're going to find the electrons. The atomic orbitals is where you're going to find specific electrons. So atomic orbitals is what happens if you, the way you build an electron cloud is you put together atomic orbitals. So it's sort of like the electron cloud is the hotel. Everybody's going to be in the hotel. But if you want to find out where a specific person is, you check out what room they were in. That would be the atomic orbital. So if you call a hotel and say, is Mr. Stevens there? They can say yes, right? Or is Mr. Stevens is in room 32? So Mr. Stevens is in room 32, atomic orbital. Mr. Stevens is in the hotel, electron cloud. One last word, sometimes they call them sub-levels, right? They're at a level, and then there's pieces of that level, the sub-level. Everybody okay at this? Okay, so light's a wave. We see rainbows. Light's an electron, photoelectric effect. Electron is a particle, photoelectric effect. It's moving individual electrons along. Electron's a wave, diffraction. Have a good one.